Total 7. Do you see my screen?
Sì.
Okay. So I will try to be very quick because I just want to share with you some of the recent research that I'm involved directly in. After the finding of this component, the cocoon, in very nearby GRB supernovae, I have started in collaboration with other external colleagues, external for foreign people mainly, a sort of program to find signature of this component, especially at radio wavelengths. So just a quick summary about core collapse supernovae. You know that very massive star, almost at the end of their lives, they show this onion-like structure with elements located at most central region of the star, with sort of with lighter elements located more externally. And you should know very well that at certain time this star is still kept in equilibrium by the radiation pressure generated by nuclear reaction in the cores versus the gravitational pressure that is trying to compress all the external layer onto the core. But at certain time, when we have an iron core, you know that iron is one of the most stable elements, and in order to ignite additional nuclear reaction, you must provide fuel, energy to the iron core. And this is cannot be provided just by the gravitational compression. So we have that in a few seconds, maybe fractional second, the iron core collapse because it cannot sustain the gravitational pressure. Will collapse into the core. The star will collapse, generating proton-neutron star emission. But this collapse generates this neutron star that is so dense that all the layer that external layer that are fall down into the core will rebound. But at the same time, this rebound will not lead to an ejection of the material because the gravitational energy is so dense that we cannot have the ejection of the supernova. And the main ingredient that will lead to the expansion of the ejecta is neutrino emission emitted during the first photoionization and neutronization process of the iron core. Neutrino will scatter with all the above layer, with the layer that are above the neutron star, proton-neutron star, leading to the ejection of the supernova emission, and also this phenomenon called thermonuclear nucleosynthesis during the passage of the shock wave through the external layer of the star. So all the elements that we observe in the absorption line in supernova spectra are freshly synthesized elements, mainly during the shockwave passage during the core collapse event. However, of course, this reasoning is true for almost all core collapse supernova. We have a large zoo of supernova core collapse events. I'm just summarizing quickly the main classes, but now with the new survey, we are finding many subclasses with multiple and different properties between different supernovae. The main two classes are type 2 and type 1b and c, and each single type is associated with a specific progenitor. We have the type 2 supernovae that show presence of hydrogen in their optical spectra, are associated with the big, large red supergiant star that still have an hydrogen layer as its most external layer of the progenitor star. Then we can have type 1b supernova, 1b because we do not have hydrogen, so it's not a type 2, it's a type 1 supernova, and b because we observe signature of the presence of helium, neutral helium absorption in the spectra. And this is an indication that the progenitor was a sort of Wolf-Rayet star of the nitrogen type that still keeps the helium layer as its most external bound layer into the core. And then we have type 1c supernova where we do not see helium, but we have clear presence of faint silicon-2 light in addition to iron, calcium, magnesium, but no hydrogen, no helium. And subclasses of these events that are associated with carbon-oxygen Wolf-Rayet star are characterized by broad lines with the large velocity that can be determined by the minimum of the absorption line, especially of silicon-2 over these big carbon or iron lines at 5,000 angstrom, which is an indication of large expansion velocity, but also large dispersion velocity. And the main reason of the presence of these large velocities, the presence of an additional central engine in addition to the canonical neutrino heating mechanism. There is another engine, which is called a central engine, that is powering the emission of these supernovae. And given that 1C broadline supernova are the only type of supernova that has been detected to be associated with gamma ray burst, there is a direct link between the presence of a central engine, jet component in general, and the progenitor of this type 1C broadline supernova. However, the properties of this progenitor are quite peculiar, because in order to have a jet component, we need to have a highly rotating black hole formed at the center of immediately after collapse, and we need a progenitor sun with a fast rotation that implies low metallicity. Why these two ingredients?
Well,
yeah, go ahead.
yes, yes. We know all this is the traditional approach, and starting everything from the black hole, but we are considering in our process a possibility that the black hole is formed only after the fourth event of the supernova system. Therefore, we will have to discuss all this, because we will need to clarify this crucial point, that the black hole, unlike this model that you are discussing,
the standard model, actually,
the standard model in which the black hole, everything starts from the black hole, our approach is different. Namely, you have a binary system to start from, and from this binary system you have a supernova, and then by the dynamic of the binary, by accretion on one of the two components of the neutron star, you reach the black hole. This is what the talk this morning of 1U showed. The black hole is, in our approach, following the supernova, and by accretion in a binary system.
So the black hole is, the black hole forms after the supernova?
Exactly. After the supernova, and is only one effect following the energetic of the supernova, the very energetic supernova following. And then by accretion of the supernova ejecta on the neutron star companion, you have the formation of the black hole. This, I think, we are quite certain, and is completely different from this approach. But I would like to discuss with you quietly, and I hope we can offer you a participation on ICRANET. That way you will be able to follow development. But at this stage, we don't need to go further on this, because definitely we have, and this is the traditional one. We don't need, we have been studied quite a lot about this, and we have a different approach, which we are proposing. Therefore, this is very crucial for us to keep going, and especially try to understand how our approach is fitting in different topic, like the red dots, and how the red dots are fitting in our scenario. Okay? Okay, thank you so much, and we keep in touch.
Okay, fine. Have a nice day.